Module 20, Lecture A, Filters, Wrappers. By the end of this lecture, you will be able to apply variance and univariate filter methods to select informative features, choose classification or regression feature scores for the target type, and use recursive feature elimination and cross-validated RFE. Filter feature selection. Variance threshold. Variance thresholding is a simple feature selection method that removes features with very little variation across observations. Features that are nearly the same for most records, such as a common customer status or a medical measurement shared by almost all patients, usually add little value for finding patterns or predicting outcomes. Because it checks each feature independently, it is a fast, easy first step before using more advanced modeling or feature selection methods. Variance thresholding removes features with little variation, and it can be used without a target variable before choosing a classification or regression approach. It is useful for spotting survey questions or sensor readings that are mostly constant and may add little information. However, low variance does not always mean low value, because rare signals such as fraud indicators can still be important. Choose a variance threshold carefully, because a low threshold may keep irrelevant features, while a high one may remove rare but useful ones. The right setting depends on the feature types and on preprocessing, since scaling and encoding can change how variance appears. Variance thresholding is best used as an early filter to reduce noise and dimensionality before applying more advanced feature selection methods. Python code, variance threshold. Variance threshold feature selection removes columns with very little variation because they usually add little useful information. The result identifies which low variance features were removed from the dataset. We import NumPy and Pandas to work with numerical data and data frames. Then bring in Scikit-Learn's variance threshold feature selector. This prepares us to remove low variance features that add little useful information, making the dataset easier to analyze efficiently. We create a small Pandas dataset with 4 features to illustrate variance in feature selection. One feature is constant, another is almost always 0, and the remaining 2 vary more naturally, such as ages and monthly visit counts. This contrast helps show how features with little or no variance differ from more informative variables. The code first verifies that the data frame has the expected size, 6 rows and 4 columns. If it does not, it raises an error to stop processing. This validation helps ensure the data is properly formatted before analysis begins. A variance threshold is used to remove features that vary too little to be useful. With a threshold of 0.2, only features whose variance is above that value are kept. The selector is fitted and applied to the dataset in one step, producing a new array with only the selected features. After applying the variance threshold, we get the names of the features that were kept. These names are then used to label a new data frame built from the selected feature data, so the reduced dataset stays clear and aligned with the original columns. We compute the variance of each feature across the dataset using the population variance formula, then round the results to 3 decimal places for readability. These values are printed so we can see how much each feature varies before applying any filtering. After applying the variance threshold, we review which features were kept and compare the dataset's shape before and after selection. This shows how many columns were removed and how many features remain, helping us understand how the threshold reduced the dataset's dimensionality. This example shows how variance thresholding can reduce a dataset by removing features that carry little or no variation. Using a threshold of 0.2, the Scikit-Learn method filters out a constant feature and another feature with almost zero variance. The script reports each feature's variance, identifies the features that remain, and compares the original and reduced dataset shapes to show the drop in dimensionality. Univariate feature selection. Univariate feature selection scores each feature separately based on how strongly it relates to the target outcome. It keeps the most informative predictors without building a full model, making it fast, scalable, and easy to interpret. This makes it useful for early exploration of datasets with many features, such as medical or marketing data. Choose a univariate feature selection score based on the type of target you are predicting. Use classification scores for categorical targets and regression scores for continuous targets, so the method matches the data and ranks features appropriately. These rankings show feature relevance, but their meaning depends on the assumptions behind the chosen statistical score. Univariate feature selection is a simple way to reduce noise before building more complex models. It keeps features that individually relate to the target, which can speed training, reduce overfitting, and improve interpretability, especially in high-dimensional data. Its main limitation is that it checks each feature alone, so it may miss useful feature combinations or keep redundant ones. It works best as an initial screening step, combined with domain knowledge and later model evaluation. Python code. Univariate feature selection. This example uses univariate scores to rank features by testing each one separately against the target. The resulting plot indicates which features are selected. We import key Python tools for a classification feature selection example. NumPy supports numerical work, Matplotlib handles plotting, and Scikit-Learn provides tools to create a synthetic classification dataset and select the best features. The feature selection uses an ANOVA F-value test to score how significant each feature is, and checking the Scikit-Learn version helps confirm compatibility. A synthetic classification dataset is created with 200 samples and 6 total features. 3 features are informative signal features, while the other 3 are noise features, with no redundant or repeated features included. A fixed random state makes the data reproducible, and shuffling is turned off, so the feature order matches the defined feature names. The code first checks that the feature data and target values have the expected sizes: 200 samples, 6 features, and 200 target entries. This confirms the dataset is properly structured before feature scoring begins. If the sizes are wrong, it raises an error, so the problem is caught early, and later analysis does not fail unexpectedly. To choose the top 3 features, use Scikit-Learn SelectKBest with the ANOVA F-value scoring method. After fitting it to the features and target, the selector identifies which features score highest. A support mask is then used to filter the feature names and return the 3 selected features. The code reports the Scikit-Learn version to support compatibility and reproducibility, then displays the selected most informative feature names in a comma-separated format. It also notes that higher F scores mean stronger separation between classes, helping explain why those features were chosen. The feature selector provides F scores that show how well each feature separates the classes. These scores are plotted as a bar chart, with selected features shown in green and unselected features in gray. The bar heights make it easy to compare feature effectiveness, while the colors quickly show which features were chosen. The plot is formatted to compare univariate feature scores from SelectKBest. It uses a clear title, labels features on the x-axis, and shows ANOVA F scores on the y-axis, where taller bars indicate stronger class separation. The feature labels are rotated for readability. The layout is adjusted to fit neatly, and the final chart makes it easy to see which features scored highest and were selected. This script shows how to use univariate feature selection in Scikit-Learn to find the most useful predictors in a synthetic classification dataset. It creates 6 features, with 3 carrying real signal and 3 acting as noise, then uses SelectKBest with an ANOVA F-test to rank them. Pause. The top 3 features are selected based on their F-scores, and the output summarizes the chosen features. Pause. A bar plot compares the scores for selected and rejected features. Percentile feature selection. Percentile feature selection keeps a chosen percentage of the highest scoring features after comparing each feature with the target. Instead of selecting a fixed number, it keeps a set proportion, such as the top 10%. This makes it a simple way to reduce dimensionality when datasets have different numbers of features, helping focus on the most relevant information in areas like medicine or customer analytics. Percentile feature selection scores each feature with a statistical test, ranks the features by usefulness, and keeps the top percentage. The scoring method should match the task, such as classification or regression. Because it evaluates features one at a time, it is fast, easy to interpret, and independent of any specific model. But it can miss feature combinations that are only informative together. Choosing a percentile for feature selection means balancing simplicity with useful information. A lower percentile removes more features and can reduce noise, but may discard important signals, while a higher percentile keeps more features and may retain irrelevant ones. Analysts usually compare percentiles with validation data to find what generalizes best, and the selection must be learned only from the training data to avoid test set bias. Python code, percentile feature selection. This example shows percentile-based feature selection for classification data. It keeps only a selected percentage of the best features, and the printed scores indicate which features are retained. We import NumPy for numerical work and use Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator for synthetic classification data, a percentile-based feature selector to keep the best features, and an F-test scoring method suited to classification tasks. We create a synthetic classification dataset using Scikit-Learn's make classification function. It contains 200 samples with 10 features, where 3 features are informative and the rest are noise. There are no redundant features, and a fixed random state is used so the dataset can be reproduced. We create a NumPy array of feature names, so selected columns can be identified more easily. The names are simple labels from feature 0 through feature 9, matching the 10 features in the dataset. We use Scikit-Learn's SelectPercentile feature selector to keep only the top 30% of features for a classification task. The features are ranked with the F-classification scoring method, and applying fit transform both learns the best features and returns a reduced dataset containing only those selected features. We expect 3 columns to remain because 30% of 10 features is 3. We then check the selected feature array's column count to confirm that the feature selection kept the correct number of features. The code verifies that feature selection returned the expected brief features. If the count is different, it raises an error, helping confirm that the selection process worked correctly. Use the selector to identify which features were kept, then filter the feature names to show only those selected. The selected features are the ones chosen based on their scores, and rounding those scores to 2 decimal places makes them easier to read. This helps compare the relative importance of the retained features. The output summarizes the feature selection results by showing the Scikit-Learn version for reproducibility, the original and selected feature counts, the names of the chosen features, and their rounded scores. Together, these details confirm which features were selected and indicate their relative importance. This script shows how percentile-based feature selection can identify the most useful inputs for a classification task. It creates synthetic data with 10 features, then uses Scikit-Learn to keep the top 30% based on an F-test score, selecting 3 features. It verifies the selected count and reports the original and reduced feature totals, the chosen feature names, and their rounded scores. Score functions. Selecting score functions. In filter-based feature selection, the score function defines how each feature is judged against the target before model training. It must match the prediction task, use a classification score for categorical targets, and a regression score for continuous targets. Choosing the wrong type can rank features based on irrelevant relationships, so matching the score function to the target is essential for meaningful feature evaluation. Score functions help detect associations between features and targets. For categorical targets, they look for feature distributions that differ across classes, while for numerical targets, they measure whether feature changes relate to higher or lower target values. The key is to choose a score function that matches the target type and the kind of signal you expect, because a feature that separates categories may not explain continuous variation well. Choose a score function that matches your target, feature types, expected relationships, and modeling goals. Some scoring methods fit numerical data, while others are better for categorical or count-based features. Simple linear scores can work for direct relationships, but may miss more complex patterns, such as effects that appear only after a threshold. Because filter scores evaluate features one at a time, they are useful for early simplification, but may overlook important feature combinations. Python code, selecting score functions. This example shows that score functions should match the target type. Classification scores are used for categories, while regression scores are used for numeric targets, leading to different but appropriate feature rankings. These imports prepare the workflow for creating synthetic machine learning datasets and selecting useful features. NumPy supports numerical array operations, while Scikit-Learn provides tools to generate classification datasets with categorical targets and regression datasets with continuous targets. The feature selection tools then compute F-values for each task type, using ANOVA for classification and a regression-based score for continuous targets. This line shows the Scikit-Learn version currently in use. Checking the version helps confirm compatibility and indicates which features or improvements are available. We create a synthetic classification dataset using Scikit-Learn's Make Classification function. The dataset has 120 samples and 5 features, with 2 features carrying useful information for predicting the category and no redundant features. A fixed random state ensures the same data is generated each time, making the example reproducible. A synthetic regression dataset is created using Scikit-Learn's Make Regression function. It includes 120 samples and 5 features, with only 2 features actually influencing the target. Added noise makes the data more realistic, while a fixed random state ensures the same dataset is produced each time. This provides a controlled dataset for testing regression models. The code first verifies that the classification and regression feature matrices have the same shape, meaning they contain the same number of samples and features. If they do not match, it raises an error. This check helps ensure a fair comparison of score functions and prevents misleading results from mismatched data. Before training or evaluating the models, we confirm that each target list has the same length as its matching dataset. This check is done for both classification and regression data, so every row has a corresponding target value. If the sizes do not match, an error is raised to prevent feature and target mismatches. We use the fclassif function to score how well each feature separates the dataset's categories and to compute related p-values. Then, we sort the features by their scores from highest to lowest, so the most useful features for classification appear first. This ranking helps identify which features contribute most to distinguishing the categories. To assess how features relate to a continuous target, use Scikit-Learn's regression scoring function to measure each feature's correlation with the target and its statistical significance. Sorting the scores from highest to lowest helps rank the features by influence. This makes it easier to identify which features are most strongly associated with the target in a regression task. We create a NumPy array of feature names, from feature 0 through feature 4, to match the features in the dataset. Keeping these names in an array makes them easy to index and helps us interpret feature selection results, especially when identifying the highest scoring features. For feature selection, use the F classification function when the target is categorical, and the F regression function when the target is numeric. In each case, rank the features by their scores, select the top 3, and report their scores rounded to 2 decimal places. The key point is to choose the scoring function that matches the type of target. This script shows how to choose the right feature scoring method based on the target type in Scikit-Learn. It uses a classification F-test for categorical targets and a regression F-test for numeric targets. Then reports the top 3 features and their scores for each case. The key point is that feature selection is more meaningful when the scoring function matches the kind of target being predicted. Classification feature scores. Classification feature scores show which input features best separate categories, such as spam and not spam. A useful feature has values that are strongly related to the class label, like blood glucose levels differing between diabetic and non-diabetic patients. Features with little class information, such as patient ID numbers, receive low scores. The goal is to identify features that naturally distinguish classes before building a model. Choose classification score functions based on the types of features and target in your data. Numerical features with categorical targets need methods that compare values across classes, while categorical features need methods that compare category distributions across class labels. Some score functions also detect broader statistical relationships beyond simple average differences. The key is to match the method to the feature and target types. Since a function suited to continuous data may not work well for text counts or binary indicators. A high feature score can suggest usefulness, but it does not guarantee better model performance. Filter-based scores judge features one at a time, so they may miss interactions or favor redundant information. Low-scoring features can still matter when combined with others, and scores may be distorted by class imbalance or data quality issues. Use these scores as guidance, then confirm choices through model training and evaluation. Python code. Classification feature scores. Compare classification feature scoring methods by matching each score to the type of feature it is designed for. In general, a higher score means the feature has a stronger association with the class label. We import NumPy and Pandas for working with arrays and data frames, and use Scikit-Learn for machine learning tools. This includes a synthetic classification data generator, feature scoring methods such as chi-square, analysis of variance, and mutual information, and a binning tool that converts continuous values into discrete categories when needed for scoring. We create a synthetic classification dataset with 300 samples and 5 unique features using Scikit-Learn's make classification function. Only 2 features are informative, while the rest do not affect the target. A fixed random state makes the dataset reproducible, giving us a controlled way to test feature selection methods. The code first verifies that the feature data has the expected size, 300 rows and 5 columns. If the dimensions are wrong, it raises an error to signal that the dataset was not generated correctly. This check helps prevent later feature scoring steps from running on improperly structured data. We give each dataset feature a clear name, from feature 0 through feature 4, so the results are easier to understand. Then we create a pandas data frame from the feature data, using those names as column headers, making later feature scores easier to interpret. ANOVA F-scores measure how strongly each numeric feature is related to the class labels. Using Scikit-Learn, the feature data and target labels are analyzed to produce F-scores and p-values. Higher F-scores suggest a feature is better at distinguishing between classes, while p-values indicate whether that relationship is statistically significant. Before applying a chi-square test, continuous features are converted into discrete bins using Scikit-Learn's K-bins discreticizer. The data is split into 5 quantile-based bins, encoded as ordered values, so each bin has roughly the same number of samples. The chi-square test then compares these binned features with the target variable, producing scores and p-values that indicate how strongly each feature is associated with the target class. Mutual information scores measure how strongly each feature depends on the target class. Using Scikit-Learn's mutual information classifier function with a fixed random state for reproducibility helps identify which features provide the most useful information about the labels, including relationships that may be more complex than linear patterns. A data frame is used to compare feature scores from 3 methods: ANOVA F-scores, chi-square scores, and mutual information scores. The scores are rounded for readability, and the feature names are used as the index, so each result is easy to identify. This makes it simple to see how strongly each feature is associated with the target class across the different scoring methods. The code ranks features by their ANOVA F-scores from highest to lowest. This makes the features most strongly related to the target class appear first, helping identify the most useful inputs for classification. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then shows the sorted target classes to summarize the classification categories. Finally, it displays the top feature scores, highlighting the features most strongly associated with the categorical target. This script compares 3 ways to score feature importance in a synthetic classification dataset with 5 features, including 2 informative ones. It uses ANOVA F-scores for numeric feature target relationships, chi-square scores after binning the features, and mutual information scores to capture broader dependencies. The results are organized and ranked to show which features are most strongly linked to the target class, along with basic output such as the Scikit-Learn version and target classes. Regression feature scores. Regression feature scores show how strongly each input relates to a continuous outcome, such as house price or hospital stay length. Features with higher scores, like square footage for house prices, provide more useful predictive information than weakly related features. The goal is to identify the inputs that help the model make more accurate predictions. Regression feature scoring often measures how strongly each feature has a linear relationship with a continuous target. This is useful when feature changes consistently match outcome changes, such as experience and salary. But some relationships are curved or depend on thresholds, so a linear score may miss important patterns. Choose the scoring method based on the expected relationship between the features and the target. Regression feature scores usually evaluate each feature separately, so they can miss important interactions between features, or overvalue features that repeat the same information. A low score does not always mean a feature is useless, and a high score does not guarantee it improves the model. Use these scores only as an initial guide. Then test the chosen features in a full modeling process to confirm they improve prediction and generalize well. Python code, regression feature scores. This example compares feature scoring methods for regression. It shows that linear and nonlinear relationships can receive different scores, and the resulting ranking helps identify which features are most important. We import NumPy and pandas to work with numerical data and data frames, then use Scikit-Learn for machine learning tools. In particular, the F-regression and mutual information regression methods help measure how important features are for a regression task. F-regression focuses on linear relationships, while mutual information regression can detect broader dependencies between features and the target. We create a small reproducible regression dataset by using a fixed random seed and setting the sample size to 200. A linear predictor is then generated by drawing 200 values from a normal distribution. The dataset is built with a perved feature drawn from a uniform range between -3 and 3, creating nonlinear structure. A mostly irrelevant noise feature is added from a normal distribution to test feature selection robustness. Additional normal noise is also added to the target to reflect real-world variability. The target variable is built to include both linear and nonlinear relationships. It combines a linear feature, a squared curved feature, and added noise to create a continuous outcome. The features are then organized in a pandas data frame, containing the linear feature, the curved feature, and a noise feature, making them easier to manage and compare with the target. The code first verifies that the feature's data has the expected size, 200 rows and 3 columns. If the dimensions are wrong, it raises an error instead of continuing. This early check helps confirm the dataset was built correctly and prevents problems during later feature scoring. We evaluate feature importance in 2 ways. First, the Scikit-Learn F-regression function measures how strongly each feature has a linear relationship with the target, using F-scores and p-values. Then, mutual information regression estimates both linear and nonlinear relationships, giving a broader view of which features may be useful. A fixed random state is used so the mutual information results are reproducible. A data frame is created to compare feature scores from 2 methods, F-regression and mutual information. Each set of scores is rounded to 2 decimal places, and the feature names are used as the index so the values line up correctly. This makes it easy to compare the linear and mutual information scores for each feature side by side. The code ranks features by mutual information to show which ones have the strongest overall relationship with the target. It also reports the Scikit-Learn version for reproducibility, then prints both F-regression and mutual information scores, so linear and nonlinear feature relationships can be compared. This script compares 2 ways to measure feature importance in regression: F-regression for linear relationships, and mutual information regression for broader, including nonlinear dependencies. It uses a synthetic dataset with a linear feature, a curved feature, and a noise feature, where only the first 2 meaningfully affect the target. The results usually show the linear feature scoring well with F-regression, the curved feature standing out more with mutual information, and the noise feature scoring low in both. It also reports the Scikit-Learn version and the feature scores to summarize which inputs are most useful for prediction. Recursive feature elimination. RFE basics. Recursive feature elimination, or RFE, selects useful features by training a model with all candidates, removing the least helpful features, and repeating until the desired number remains. Because it evaluates features within a specific model, it can account for interactions that simpler filter methods may miss. The goal is to keep a smaller set of features that support strong prediction, while removing features that add little value or unnecessary complexity. Recursive feature elimination uses a model to judge which features matter most, such as coefficients in linear models or split quality in tree-based models. It removes the least important features, retrains the model, and repeats because feature importance can change when other features are removed. This makes RFE an iterative search for the best feature subset, not just a single ranking. In recursive feature elimination, the key choices are how many features to remove at each step and how many to keep in the final model. Removing features one by one is more careful, but slower, while removing groups is faster, but may discard useful information. The final feature set should balance domain knowledge, simplicity, computing limits, and validation results. Proper validation is essential to avoid overfitting and ensure the selected features work well on new data. Python code, RFE Basics. This example introduces recursive feature elimination, a method that uses a model to repeatedly remove the weakest features. The result identifies the selected features and reports the model's test accuracy. We import key Scikit-Learn tools for a machine learning workflow using the breast cancer dataset. These include tools to split the data, standardize features, build a pipeline, select important features with recursive feature elimination, train a logistic regression model, and measure performance with accuracy. Together, these imports support preparing the data, choosing useful features, training the classifier, and evaluating its results. We load Scikit-Learn's breast cancer dataset, a common example for classification tasks. The dataset is separated into input features for the model and target labels for each sample. We also keep the feature names so we can identify selected features later. The code verifies that the feature data and target labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error to stop training or evaluation with misaligned data, which could produce incorrect results. The dataset is split into training and testing sets to avoid test data leaking into model training, and to keep evaluation reliable. Using Scikit-Learn's train-test split, 25% of the data is reserved for testing, and the rest for training. Stratifying by the target keeps class proportions consistent in both sets, and a fixed random state makes the split reproducible. A logistic regression model is first set up to provide feature rankings for recursive feature elimination. It uses a fixed random state for reproducibility and is configured to allow enough iterations to converge. Recursive feature elimination then uses this model to select the 5 most important features, removing 2 features at a time until that target is reached. This pipeline combines feature scaling, feature selection, and model training into one clean workflow. It first normalizes the features, then uses recursive feature elimination with logistic regression to keep the most important ones, and finally trains the logistic regression classifier. Because each step is fit only on the training data, the process helps prevent data leakage. The pipeline is trained on the training data by scaling the features, selecting the most useful ones with recursive feature elimination, and fitting a logistic regression model. The trained model then predicts labels for the test data, and its accuracy is measured by comparing those predictions with the true test labels. After training, we can see which features recursive feature elimination kept by retrieving its support mask from the pipeline. This mask marks the retained features, which we use to filter the original feature names. The result is a concise list of the features the model considered most useful for prediction. The output summarizes the feature selection results by showing the Scikit-Learn version, the original feature count, and how many features were kept after recursive feature elimination. It also names the selected features and reports the test accuracy using only those features, rounded to 3 decimal places, to show whether the reduced feature set still performs well. This script uses logistic regression with recursive feature elimination on the breast cancer dataset. It splits the data to avoid leakage, scales the features, selects the 5 most informative ones, and trains the model. It then reports the Scikit-Learn version, the original and selected feature counts, the selected feature names, and the test accuracy rounded to 3 decimals. The example shows how feature selection can focus a model on the most useful attributes. Cross-validated RFE. Cross-validated recursive feature elimination chooses how many features to keep by testing prediction performance across multiple data splits. Instead of simply removing the least important features until a fixed number remains, it checks how performance changes as features are removed. This helps find a smaller feature set that still predicts reliably on new, unseen data. Cross-validated recursive feature elimination selects features by repeatedly removing weaker ones and checking how model performance changes across different data splits. If accuracy stays stable with fewer features, a simpler model may be enough. If performance drops, important information was likely removed. This approach helps identify the most useful inputs in areas such as medical risk prediction, customer churn modeling, and engineering sensor analysis. Cross-validated recursive feature elimination selects the best feature subset for a specific model, metric, and dataset, not a universally best set. Its results can change if the estimator, evaluation measure, or data sample changes. Although it requires more computation because it repeatedly fits models, it gives a stronger basis for choosing features when simplicity, interpretability, or cost matters. It is useful for balancing predictive performance with a smaller, more practical feature set. Python code, cross-validated RFE. Cross-validated recursive feature elimination selects the best number of features by comparing validation accuracy across different feature subsets. The accuracy trend helps show how performance changes as more features are kept. We import key Python libraries for the workflow: NumPy for numerical operations, Matplotlib for plotting, and Scikit-Learn for machine learning tools. We also use Scikit-Learn's classification data generator to create synthetic data for testing feature selection. We import key Scikit-Learn tools to build a streamlined feature selection workflow. Recursive feature elimination with cross-validation chooses the best number of features, logistic regression ranks them as the classifier, and stratified k-fold keeps class proportions consistent during evaluation. A pipeline then combines steps like scaling and feature selection into one simpler model fitting process. The code imports Scikit-Learn's standard scaling tool, which standardizes features by removing their mean and scaling them to unit variance. This helps machine learning models treat features more evenly, especially when the data uses different units or scales. We create a synthetic classification dataset with 500 samples and 12 features using Scikit-Learn. Only 4 features are truly informative, while 2 are redundant combinations of those useful features. A fixed random seed ensures the results can be reproduced. This setup mimics a realistic case where some features help prediction and others do not, making it useful for testing feature selection methods. Before modeling, the code verifies that the feature data has 500 rows and 12 columns. If the dimensions are different, it raises an error to stop processing. This check helps ensure the data is properly structured before analysis begins. A logistic regression model is used as the linear classifier, with a fixed random state for reproducible results. Recursive feature elimination with cross-validation then ranks the features by removing the least important ones, one at a time. The process uses 5-fold stratified cross-validation, with shuffled folds to preserve class balance, and accuracy is used to measure performance. We build a pipeline that first standardizes the features so they share a common scale, then uses recursive feature elimination with cross-validation to choose the most useful features. Fitting the pipeline applies scaling, feature selection, and model training together in one process. This helps create a more efficient model by selecting features based on cross-validated accuracy. Extract the trained recursive feature elimination with cross-validation selector from the pipeline. Then, check how many features it kept. To make the selected features easier to identify, create simple feature names using the letter F followed by each feature's index across the dataset. We take the average validation accuracy scores from recursive feature elimination and match them with the number of features tested. This lets us compare feature count against accuracy and prepare the data for plotting that relationship. The code reports the Scikit-Learn version to confirm the working environment, then shows how many features were selected by recursive feature elimination with cross-validation. It also prints the selected feature names by using the fitted selector to identify which features were kept. Create a plot showing how mean validation accuracy changes as the number of selected features varies. Use markers to show each feature count. Then add a red dashed vertical line at the feature count chosen by recursive feature elimination with cross-validation. This highlights the number of features that produce the best cross-validated accuracy. The plot is labeled to show how validation accuracy changes as different numbers of features are kept. The x-axis represents the retained features, and the y-axis shows mean cross-validation accuracy. A legend helps identify key elements, including the marker for the optimal feature count, selected by recursive feature elimination. The plot is displayed to show how validation accuracy changes as different numbers of features are kept. This visual summary of recursive feature elimination helps identify the feature count that gives the best cross-validated accuracy. This script uses logistic regression with recursive feature elimination and cross-validation to choose the best feature subset from a synthetic dataset. It scales the data, applies stratified cross-validation, and selects the number of features that gives the strongest accuracy. It then reports the selected features and plots how accuracy changes as more features are kept. Wrapper cost. Recursive feature elimination is useful because it judges features by how they affect a predictive model, rather than evaluating them alone. Its main drawback is cost. Each removed feature requires retraining the model, which can become slow with many features or complex models. Beyond computation time, it also adds work in managing experiments and checking that the selected features are stable. Combining recursive feature elimination with cross-validation gives more reliable feature selection because each subset is tested across multiple data splits rather than one sample. The trade-off is much higher computation, since the model must be retrained many times at each feature removal stage. This can help identify important predictors, such as key lab measurements in medical tasks, but it is slower than simpler one-time feature ranking methods. Recursive feature elimination can be computationally expensive, so use it strategically. First, reduce the feature set with simpler methods or domain knowledge, removing redundant or irrelevant inputs before applying it. Choose an estimator that offers a practical balance between accuracy and speed, aiming for feature selection that is reliable, understandable, and efficient within your resources. In this lecture, you learned to apply variance and univariate filter methods to select informative features, choose classification or regression feature scores for the target type, and use recursive feature elimination and cross-validated RFE. In the next lecture, Lecture B, we will go over embedded sequential.
Thank you for your attention. See you all in the next lecture.